Okay. Now, how was that anomaly, okay, the disagreement between the predictions of physics with reality, how was that resolved? Well, basically what that meant was the physics at that time that we used to make that prediction, the Rayleigh-Jeans equation is wrong, right? So if you recall, the Rayleigh-Jeans equation says that the spectral density is equal to this, right? This is the number of cavity modes per unit volume per unit frequency times the average energy of the oscillator. And the Rayleigh-Jeans equation says that the average energy of the oscillators would be kT. So to try to explain the blackbody spectrum, Max Planck made a very radical assumption. He made the assumption that the energy of the oscillators is quantized. Okay, what does quantized mean? It's restricted. Okay, it cannot have just any value. It's restricted to certain allowed values. It's like money is quantized. You can have 1 cent, 2 cents. You cannot have 1.1 cents. There's jumps in between, right? So according to Planck, okay, you can explain the blackbody spectrum if you assume that the energy of oscillators is quantized and proportional to the frequency. So he said it's equal to some constant h times the frequency nu, and it's a multiple of that. So n here is 1, 2, 3, 4. So it can be h nu, 2h nu, 3h nu, and so on. Okay? So that's what quantized means. For example, let's say h nu was 3 electron volts, then that means the energy can either be 3 electron volts. If it were to absorb energy, if it were to gain energy, it has to gain at least 3 to bring it up to 6. It cannot have 4. It cannot. So if it has 3 electron volts, and you gave it 1 electron volt of energy from light, it won't take it. If you give it 2 electron volts, it won't take it. If you give it 3 electron volts, it will take it up to 6. It will be able to stretch further. Okay. If you want it to be to gain some more energy, what's the next amount of energy it can have? Another 3 electron volts would bring it to 9 electron volts. So it would be a multiple of h nu. Okay, so if h nu is 2 electron volts, okay, if it were to gain energy, it has to end up at 4, or at 6, or at 8. So it has to be a multiple of h nu. Okay, if that is the case, okay, Planck was able to show that the energy of the oscillator would be the average energy of the oscillator would be equal to h nu over e to the x minus 1. So it's h nu over e to the x. X hat is defined to be h nu over kt, where kt is Boltzmann's constant minus 1. So instead of just kt here, this is no longer kt. This average energy of the oscillator is h nu over e to the h nu over kt minus 1. Okay? So this is Planck's prediction of what the blackbody radiation is. The spectrum from the blackbody is going to be if the energy of the oscillators are quantized. Okay, so let's take a look at that equation. That equation actually does agree with the experimental blackbody spectrum. Okay, let's see how that agrees. Okay, with experimental data. What happens as nu approaches infinity? What did we say the spectrum looks like? It goes up and then goes back down, right? Versus frequency, right? And Rayleigh-Jeans equation, the classical prediction says it agrees at low frequency, right? But it fails at high frequency. This is versus frequency. Okay. So let's examine this expression right here. 8 pi nu squared over c cubed. Okay. What happens as frequency approaches infinity? This goes to infinity, right? So this term approaches infinity. But what about h nu over e to the x minus 1? What happens to that? This one, you have an exponential term raised to to the x, but x is just h nu over kt. You have an exponential term raised to an expression involving nu. So e to the x is going to approach a very large number, right? As nu approaches infinity. So this entire expression right here is going to approach 0. So when you multiply two things, one approaching infinity, but the other one approaching 0, since this term has this thing that approaches 0 is exponential, it goes to 0 faster than this other one can go to infinity. So what ends up happening is eventually this second term wins out over here at high frequency. So the intensity goes back down to 0 eventually. And so you have that maximum. Now, what's the physical interpretation of that? Basically, what this is saying is that if you have high frequency oscillators, okay, those are the picky ones, right? They're not just going to take any amount of energy. If an oscillator has an energy of 10 electron volts, it's not going to accept 1 electron volt. It's not going to accept 2 electron volts. It needs at least 10 and then 20, right? So they're less likely to gain energy because they're going to need more energy before you can excite them. Okay, so when you say an oscillator gains energy, we say it's excited. For you to excite a high-frequency oscillator, you need more energy. So they're less likely to gain energy. So they're going to contribute less to the average energy of the oscillator. Your very high-frequency oscillator can emit very high-frequency. There are fewer of them that can emit. There's fewer high-energy. There's fewer excited oscillators that have a high frequency, right? So that means their contribution to the average energy of the oscillators would be less. Yes. Okay. If you have fewer A's in your transcript, then your average would be the A's won't contribute as much to your average, and that's another way of looking at it. Okay. So that's the physical explanation for that.